We start with the Clapeyron equation for the vaporization process. So delta H and delta V on the previous slide are the molar enthalpy of vaporization and the change in molar volume for the vaporization process, respectively. We rewrite Clapeyron equation as dP equal delta H vaporization divided by T times delta vaporization V times dt. Delta vaporization V is equal to Vmg minus Vml, or the difference between the molar volume for the vapor and the molar volume for the liquid. We have already learned that the molar volume of the liquid can be neglected when compared to the molar volume of the vapor phase. So delta vaporization V can be approximated as the molar volume of the vapor phase, which, using the ideal gas law, we can write as RT over P. So replacing delta vaporization V by RT over P, we get dP equals delta vaporization H divided by RT squared over P times dt, which we can rearrange as dP equals delta vaporization H times P times dt divided by RT squared. This equation is rearranged one last time to separate the variables P and T, so it can be integrated between the initial state T1 and P1 and the final state T2 and P2. The integration assumes that the molar vaporization enthalpy change is independent of pressure and temperature and equal to the standard vaporization enthalpy at the normal boiling temperature. The integration leads to natural logarithm of the ratio P2 over P1 equal to minus delta vaporization H divided by R times 1 over T2 minus 1 over T1. This equation is known as the Clausius-Clapeyron equation. We now consider the solid-vapor phase equilibrium. Delta H and delta V are the standard sublimation enthalpy and the change in molar volume upon sublimation, respectively. The derivation on this slide follows literally the one we just carried out for the vaporization process. We assumed the molar volume of the vapor to be much larger than that of the solid, and using the ideal gas law, we express Vm vapor in terms of temperature and pressure, and obtain, after rearrangement, dP over P equals delta H sublimation divided by RT squared times dt, which we integrate between an initial state defined by temperature T1 and pressure P1 and a final state defined by temperature T2 and pressure P2. Again, we assume that the molar sublimation enthalpy change is independent of pressure and temperature and equal to the sublimation enthalpy change near the triple point. For the liquid vapor and solid vapor coexistence curves, we neglected the molar volume of the condensed phase, solid or liquid, in comparison to that of the vapor phase. For the solid-liquid equilibrium, no such approximation can be made, and the molar volumes for the liquid and solid phases will need to be calculated from the respective densities and molar mass, which of course we can find in the literature. So, starting from the Clapeyron equation and separating the variables P and T leads to dP equals ratio of the molar enthalpy change to the molar volume change for fusion times dt over T. If we make the assumption that the solid and liquid molar volumes or densities are independent of the pressure and temperature, then we can integrate this differential equation and obtain P2 minus P1 equal to the ratio of the change in molar enthalpy to change in molar volume for the fusion process times the natural logarithm of the ratio T2 over T1. In all instances, the enthalpy of fusion is positive since heat needs to be transferred into a crystal to melt that crystal. Now, for most substances, the molar volume of the liquid phase is larger than that for the solid phase, since the liquid density is typically lower than the solid density. Hence, an increase in pressure, P2 greater than P1, leads generally to an increase in the temperature of fusion. Natural logarithm is positive, which implies that T2 over T1 is greater than unity. The melting behavior of ice and the crystallization of water, however, follow a different trend, since the density of ice around 0 degrees Celsius is lower than the density of liquid water. As a consequence, an increase in pressure leads to a decrease in the melting temperature of ice crystals.